We'll make a start, Jarred. Good morning again to those that just joined. My name's Rick Nord, Global Technologies Manager at Nexxis. Thanks for joining. A couple of familiar names I see there, but we've got Jarred Asquith as well, Senior Solutions Engineer, just on the other side. We'll be sharing a custom robotic solution with an NDT method that was recently deployed by Nexxis. A couple of options if you want to ask questions, just please ask them along the way. So there's a Q&A button on the bottom of your screen. You can click on that and type away. There's a chat button, you can click on that and type away, or then the last option, you've got a raise your hand feature as well. And then just between each slide, I'll just allow you to speak, and then you just take it away and ask questions as we go. There's a few more trying to join, Jarred, but I think if we get started, if you introduce yourself and take it away, please, mate.
Cool, thanks, Rick. A few familiar faces there in the attendees, but my name's Jarred Asquith. I'm a Senior Solutions Engineer at Nexxis. Most of what I do is around the integration of NDT methods into robotics and the complex scopes and trialing technologies on site. So along those lines, kind of what we're talking about today. First of all, I'll just go through a quick company introduction, sort of 5 minutes, just explain who we are at Nexxis. And then we'll go into the Dam Dissipator, just what we did there to inspect it, and then a few questions at the end and what's coming up. Rick's kind of covered it, but we like to keep these pretty open, pretty casual. So just flag questions, and we're happy to stop and ask. We find sometimes they kind of help go down a path that we otherwise wouldn't have sort of approached, and it gets us some good conversation. So yeah, don't hesitate to ask questions. So Nexxis, sorry, just sorting out my screen here. We started in 2014, so about 6 years old now. We started off as a purely sort of a equipment rental. Mostly in the NDT and RVI space. So we're talking borescopes and UT sets and those sort of things. Through that, like a couple of years in, we started getting into robotics, mainly for pipe inspection, sewer cams, those sort of things. And we started to tie with our oil and gas and sort of mining and energy industries, bringing these sort of sewer cameras to do pipe inspections. And from that, we sort of started to hit the limitations pretty quickly on what they can and can't do. And then from that, we created a few partners like GE, Eddyfi Inspection Robotics, Cyro, some universities here in WA and across Australia, where we started looking at different technologies and sort of bringing them in to fill the gap of where we were sort of seeing shortfalls from off-the-shelf products. And so from then, like the last sort of 2 years, we've really taken off as a company. We've gone from, I've been in the company about 3 years, and we were employee number 8, I think, and now we're up to about 55. We're in 3 locations now, so Perth is our main operations. We have a office in Singapore, and then we have a fast-growing office in Houston, all doing the same sort of approach. So we're renting, supplying technology to a range of industries, but mostly around the sort of inspection space. To support us, we've created 3 revenue streams. So the first one is engineering. So as we've grown as a business and sort of worked on moving away from that off-the-shelf stuff to customization and sort of meeting niche scopes, we've sort of found this need for a workshop where we can rapidly prototype, we can design, we can test, we can build prototypes, we can build test pieces, and we can do it all in-house pretty quickly. So to support that, we bought a machine shop about 1.5 years, 2 years ago now. Full 400 square metre machine shop. It's off-site from our office here in Perth. And through that, it kind of gave us the ability to go to the next step and in prototyping and sort of custom designs and really sort of bring solutions to clients and market really quickly. So Nexxis is obviously the sort of banner Rick, myself, and most of the engineering team work under. We kind of break the business up into a couple of areas. So we have the sort of the finance, where we're renting, leasing, those sort of things, and kind of helping customers with the best sort of solution on that front. Then we also have the sort of pure NDT guys. So we have a PhD in materials science. We have quite a strong team on the sort of UT, X-ray, all that sort of stuff. And then we've got the sort of robotic solutions and RBI team, which is where kind of a few of us engineers sit. And through that, we're doing a lot of consulting work on what equipment will suit what scope best, those sort of things, modeling how cameras and equipment will perform in the field. Yeah. And then last, to just support our business, we noticed that it was quite easy to rent out a robotic crawler, that you'd rent it to a technician or someone who's never used it before. They might have a remote control car at home that they play with or something, but they've never driven an expensive robotic crawler and generally in quite a complex situation. So we created Lab 61. So Lab 61 is a registered training organisation, and we're really focusing on deployment of robotics and RVI techniques. We're kind of staying away from the NDT because that's well covered already. But with the RVI, so we're showing sort of what equipment works better where, how to scope a job, what are the requirements to get the best results for certain damage mechanisms, those sort of things. And then for the robotics, we're kind of looking at the holistic view of an inspection. So quite often you'll get a crawler or a robotic solution, you'll get some product training and familiarization on how to operate that set product. But what they don't cover is how to actually deploy that product, how to recover that product, how to scope if that's actually the best product for this vessel or for this pipe. We noticed a big limitation there, and that's where Lab 61's come in. So we've built kind of supporters through a lot of our custom projects, but we've got a bunch of samples, test vessels here in Perth, and one of the largest fleets of robotics, inspection robotics in the world. And so when we train, we kind of pull everything out. We can put different crawlers, different systems in different scenarios, and just see how they perform and really kind of show that holistic view of how to pull off a robotic suit inspection. So that's the kind of it for the company introduction.
Just a quick one. Just got the first question through. It's a Singapore-based question. Is all the equipment only based in Australia? You've mentioned the two other offices, is obviously Singapore and Houston. Is the equipment easily deployable to each one of those, or how does that side of it work?
Yeah. Obviously, the majority of equipment here in Australia, but what we do is when we started each office, we gave them portions of each equipment. So Singapore's got a full range of equipment, and then from there we support them. So like we don't sort of charge for shipping and then international fees. Like we'll do it out of Singapore to the client or out of Houston to the client, and we're building up the repertoire of equipment in both places. But both places do have their own equipment and do have a fair bit of equipment already, and we're constantly growing that on a needs basis. Yeah, that's a good question. Cool. If there's no more questions, we'll jump into the Dam Dissipator inspection.
Ready to start, Jarred? All good.
Cool. So this was a scope that came to us through a sort of engineering consulting service company and water distributor in the East Coast, New South Wales. The issue was they have a dissipator, and I've got some drawings a little bit further on. It was reasonably large. Well, in terms of dam dissipator or spillways, it's pretty small in terms of an asset to inspect. it was reasonably large. So we're talking about 12 meters long, about 9 meters in diameter. And we were allowed in the dissipator at the time, like we could fully isolate it. But the idea was they didn't want to put scaffolding in to reach the roof and the upper edges where they wanted to inspect. They had quite a thick steel plate, which we'll look at, which is about 19 mils. They're looking for far side corrosion. The asset had been in the ground about 20 years, and then there was a bit of an extension on it, which had been in the ground about 10 years. And then the reason they wouldn't do a conventional technique, and we'll cover that a little bit, was there was a lacquer coating on it, which would sort of rule out the more typical approach of a UT. So we'll get some drawings and stuff and make the slides a bit more exciting. But the sort of first part we do is client, service company, engineering, consulting kind of dump the scope on us and just ask us, like, what would we do? How would we do it? Here are the limitations. For us, it was very clear-cut limitations. They wanted to inspect, they didn't want 100% coverage. They wanted to inspect risky areas that were identified by their engineering team. They wanted to not have to build scaffolding. We're allowed guys in the asset at the time because we could fully isolate it. And they basically wanted to know if there was corrosion, how significant it was, and if they could get away without having to re-lacquer it. And one of the issues with this was that it was, for those who aren't familiar, it's here's a kind of drawing photo of it. We'll go back. So what it is a big sort of U-shaped steel can, and then behind it they've poured concrete. And so the concern here for the client was that waters come between the steel and the concrete, and that's why they were getting corrosion on the external side. And then they've obviously, it's a little bit hard to see on the photo, but there's a lot of little patches with over sort of previous inspections, they've grinded off blisters and painted them. And they wanted to sort of have a look at those as well and see what the risks were there. So what we came up with, like we look at kind of all the techniques when we get a scope like this. So we looked at UT. Like I said, there was a coating on the surface, which kind of UT could work. It would have been a little bit trickier and not sort of the greatest. Plus there's the water and the coupling that you have to deal with. So we kind of settled for a technique called pulse eddy current, which we'll kind of cover in the next couple of slides. And then we looked at how we'd integrate that onto a robotic crawler and use the sort of a magnetic robotic crawler to climb up the walls and do the inspection. So kind of the first thing we do is once we're kind of happy with the client, like, and explain the technology to the client and sort of happy with our proposed solution, we just draw it and model it. So this is the crawler that we use. Most of it is off the shelf. So we've got the tracks, the camera, just a standard crawler that we have. And then we put in the probe and the 3D printed mount to hold it. So what we're looking at when we're simulating it is we didn't create the asset, we just created a wall, we drove it up and down. We wanted to see if there was any areas where if we're going over welds or that the crawler would fall off. And that's really what we're simulating for this scenario. Myself, I'm actually one of the trainers in pulse eddy current for Australia. So I was a little bit biased towards going down that technique because I understood it quite well. So pulse eddy current sort of just seemed to be the right solution for us. The probes themselves are quite big, quite heavy. So again, it was just important for us to identify how that would work. And then one of the other sort of major concerns we had when we're simulating this and evaluating this scope was how would driving a magnetic crawler, so this crawler here has got permanent magnets down the side, how driving that crawler would affect the pulse eddy current result. Pulse eddy current is an electromagnetic technique, so any introduction of magnets are going to sort of offset your results a little bit. So we had to do a bit of simulation and trials just to prove that the data that we would get in situ would be sort of accurate and what we wanted. So
just a couple of questions, Jarred, if you don't mind. You've mentioned these have been in service for some time. Has there other inspections been carried out?
Yes, there were inspections carried out. What they were doing is, I'm not sure if I got a photo of it here, but they had some lugs welded on the sides, and they were bringing in scaffolding from the roof and building platforms, about a sort of 2 levels of platform, and then had a guy walking around with a grinder and UT basically. So quite a lengthy, quite a lot of work for an inspection. Probably the more traditional approach of how these things are assessed. But yeah, that's what they've been doing. They hadn't looked at this particular asset, I believe, for about 5 years at the time we looked at it. So since they did the newer installation, I think they did one check on it since it was installed. So about 5 years. And again, their key thing was they didn't want to put scaffolding in because it would be offline for a significant period of time. Probably a key bit of information. So this is New South Wales, rural New South Wales. We did this right at the peak of the fires as well. So this dam, the dissipator, was feeding a agricultural stream. So it was kind of critical water going to the farmers. And New South Wales Water couldn't put it offline for more than sort of 48 hours. So it was quite a short time frame to get the inspection done. Yeah, I might just pause there before we go into the eddy current, if there's any more sort of scope questions there.
There's a couple more. I think you've answered one of those potentially already, but so it was ultrasonics grinding away and then do ultrasonics?
Yeah, so grinding, ultrasonics and recoding. Yeah, so a little bit of work plus the scaffolding. Okay,
and then I'm not sure if you know this one, but the question came on, how often does this asset need to be inspected?
I'm not sure there's any standards or guidelines to how often this had to be inspected. The way the client, or New South Wales Water, approach these projects is by a sort of major project team. And so they obviously identified this as it passed its critical time of not having an inspection, and the methods of how they were inspecting it had changed. So they wanted to kind of push forward this way. But from my understanding, there was no critical time frame. It's not like a in-service diesel tank or a diesel tank or anything like that.
Just two more, mate.
Yep.
I guess this comes back more as an overall Nexxis approach, custom crawler integration. Maybe talk about how that would normally work and some lead times associated with that.
Yeah, cool. So first of all, custom's not always the best solution, and we don't always want to run to that. Custom is when you evaluate the scope and nothing that we have or nothing we can get off the shelf will work. There's no point in reinventing the wheel and each time. So it's not all about custom, but we do a lot of custom because robotics is reasonably new in these applications. The lead times vary. So this one, the discussions went on for quite a while, 6 months or so, like most sort of complex or custom scopes. The actual delivery of it happened over Christmas, and from woe to sort of go, it was, well, go to woe, I guess, was, I'd say about 3 weeks. So it was 3 weeks of us evaluating, sort of exactly what tool, testing that tech would work with the magnet, seeing if the crawler would fall or not fall, designing and building the 3D mount and sort of having the overall package. And then also then was scan plans, how would we roll it out on site, what are required on site, those sort of things. So not a huge lead time on this, but it was sort of a lot of work on our end to deliver it that quickly, and that's not really where we like to be. We like to sort of have a bit more fat in the budget than the time budget. Was there one more question there?
Yeah, there is one more, mate. I guess it helped having a lot of the kit off the shelf, though. When I think it was a couple of slides back, you talked about the track sort of being off the shelf. Obviously, the NDT method. It's just integrating those and making sure it works, which will cut down on that lead time a little bit.
Yeah.
And the only other question here was, I guess it's a comparison between the conventional method, which was grinding the coating away and doing UT scaffolding, the whole scope, compared to how long this scope would take. You're saying it was quicker and they didn't want to shut it down for long. Do you have a comparison on how long the conventional method would take compared to the custom one that Nexxis did?
Yeah, so we were in the asset for 2 days, and that was quite a lot of time. And we found ourselves just, the client at the time just highlighting more and more they wanted to do in the last sort of half day, just while we're there. Anecdotally, again, like I've never been there when they've inspected it traditionally. Anecdotally, they were sort of talking about a week, and that was scaffolding, similar sort of coverage, and then recoating. And if you think about that, you're a day or two to put scaffolding and set it up, a day or two in the asset with a grinder and a UT, and then a day sort of recoating and settling it before you can and then taking scaffolding out before you can bring it back online. So about a week is anecdotally kind of where they were talking.
Thanks, Jarred. You can push on. Thanks, man.
Cool. So first of all, pulse eddy current. I think it's good just to give you guys a quick rundown on what it is. So it's a technique that's used. It was originally developed by Shell and Aplu, and then the sort of patent ran out on it a few years back, and it's come to market quite heavily with a bunch of different suppliers making different kits for it. The technique itself is designed for CUI, so corrosion under insulation. So what the system does is it generates an electromagnetic field, which will create sort of eddy currents in a ferrous asset or a ferrous sample or whatever we're inspecting, and then it will quickly turn off, and then we'll measure the decay, so a little impedance measure as the magnetic field's decaying. And then what you find is, if you have a solid piece, no corrosion, you get a nice steady decay. When you start getting corrosion or wall loss, because you've got less mass that's affected by the magnetic field would dissipate through that a lot quicker. And so you start seeing a sort of a different shaped curve. And that gives you the ability to kind of, I wouldn't say measure, but definitely sort of identify corrosion with a sort of a reasonable level of accuracy through coatings, through lift off. And we're talking all the way up to 300 mils of lift off, as long as it's not ferrous. So quite a good technique. Not as good as UT for a sort of a quantitative technique. UT just is miles ahead in that aspect, but as a identifying corrosion and giving yourself a reasonably good indication and sort of idea of wall loss, it works well there. So here's just a sort of a example. This was done in the lab. It's just showing UT data, so taken internally, and then this is just a wrapped carbon steel pipe, and then showing what pulse eddy current looks like on the outside. So getting similar results, but again, this is a really good situation for a sort of example. I've got a quick little video, and I'll just talk you through it. Hopefully everyone can see this as it comes up. So this is what the probe looks like. What we've got here is some sort of non-ferrous lift-off and then a pipe that we're measuring, so just a carbon steel pipe. What the probe does is it will first sort of excite, so generate an electromagnetic field. So we've got some big coils in here. We basically run a current through them, and then we get electromagnetic field. And then what that does is create eddy currents in here, which create another sort of perpendicular magnetic field. And then that's the easy part. The next part is we turn off the probe. So the probe turns off quite quickly, quite hard with electronics to sort of shut down really quickly. And then we sort of listen for the decaying magnetic field. And what that will do is change the impedance in the coils, and then we can measure that. So then when we come across to a bit with corrosion in it, we exact same process, but we'll see a sort of a quicker decay on the field, and that's kind of what that little A scan down the bottom's showing. So that's in a sort of 30 seconds what pulse eddy current is and how it works. And I thought I'd just explain that because it makes a sort of bit of sense why we went down that path. And then this is a kind of one more good sort of slide for pulse eddy current, is it just shows you the limitations of it. So when you've got significant corrosion, you actually get quite accurate data because you're measuring a sort of a volumetric loss. If you've got sort of isolated or small bits of corrosion or pits you won't see at all. Light corrosion, you'll tend to undersize. So it's just a one to kind of be aware of with pulse eddy current. So I'm going to talk about what we actually. Yeah, I was about to stop for questions. So.
Yeah, thanks, man. I guess it's more a UT-based question almost, but it's just talking about so UT with the resolution can go quite low. The question's based on the resolution for the pulse eddy current system. Frequency doesn't matter in this case, but maybe if you just explain the 3 or 4 different probes, why we'd use different ones, and then maybe talk a little bit about the footprint sizes.
Yeah. So frequency, yeah, Rick kind of touched on it. Frequency is not a thing with pulse eddy current as much. It's more, how to explain it? It's like if you had a torch and you're shining a torch on a surface, you're going to get this nice little round circle. So that's your footprint. And realistically, what you're measuring, if I cut that circle out of the material, that's what you're measuring. So it's a volumetric wall loss. As you increase the lift off, like a torch on a surface, that beam spread is going to get bigger. And also, as you increase the thickness of the material, you're going to need a bigger beam to sort of capture the whole material. So PEC, the smallest area you generally get will be around about 32 mil in diameter, and then that's volumetric, so for the whole thickness of the material you're measuring. For this scope, from memory, I think we're talking about 76 mils diameter. So if you think about our sort of spread or our area that we're interested in, every reading we took with pulse eddy current was about a 76 diameter circle. And then we're looking at the volumetric loss in that. Again, accuracies are really kind of a little bit hard to quantify with that. If you have widespread corrosion like the photo there or the image there, we'll get really good accuracy over that sort of 76 footprint. If we have sort of isolated or corrosion that's not covering that whole footprint, then we'll tend to undersize the defects. So you do get some inaccuracies. Usually we work in sort of volumetrically about 10% of the footprint. So I hope that covers that question. I'm more than happy to kind of go into some detail if there is someone who's very interested in PEC about that at a later date.
Maybe just to expand a little bit on that one, Jarred, maybe the wall thickness range and the insulation coating lift-off range for the 3 or 4 different probes?
Yeah, so sorry, I didn't cover the probe. So in the standard probe range for pulse eddy current, there's 3. So there's a small probe, which is kind of your normal stuff. So you're doing a couple inches of lift off and up to about sort of 12, 15 mils of wall thickness. Then you go into a medium probe, which we used for this job. That's when you're in that sort of thicker wall thickness. So we were at 19 millimeters wall thickness for this job. And it can handle a sort of higher range of lift off. And then there's also a sort of full large probe, which is probably about sort of 250 mils long, quite a big probe. And that's for your sort of really thick or really high lift off situations. It's hard to sort of say this probe's for this situation because it's all a relationship. So if you have a thicker wall but little lift off, you might get away with a smaller probe. If you have a thick wall with lots of lift off, you'll need the bigger probe. If you have a thin wall with lots of lift off, you might need the medium probe. So it's hard to sort of say what probe will exactly fit generically. It's more scope dependent. And usually when the system goes out, we will send all the probes with it. For this situation, I did the sort of calculations and worked out that the medium probe was well suited for the scope.
Just another one more on the workings of the pulse eddy current system. Does the data come back live? How long does it take to take a reading?
Yep, good question. Data's live. I've got some sort of results at the end of the slide, and they're visual. You get a nice sort of heat map C-scan, and they come up instantly live. So pulse with the scan depends on, again, insulation and wall thickness. But usually in sort of most common examples that we use it in, or scenarios we use it in, we're talking up to about 12 mils of wall thickness and maybe 50 to 100 mils of insulation. We'll see pulses around about sort of 300 milliseconds to 600 milliseconds. And that's usually taking 2 or 3 pulses and averaging it out on one reading. And that's just to kind of move any noise or anything from that acquisition. So quite a fast technique. The technique slows down a lot once you get onto thicker plate. So this was 19 mil, and I think we were talking about sort of 700 to 800 milliseconds per reading, per acquisition, sorry, so 2 readings on the Dam Dissipator. Cool, hope that answers the question.
They're good questions as well, appreciate that. You can move on as well, thanks, Jarred.
Cool. So we'll go through the solution. I always find it better to talk about the actual crawler with it in front of us. So this is it. This is what we use. This is it stuck to the Dam Dissipator. So this here is a barrel camera. So it's an HD 10 times optical zoom. The little eyes on it make it look like a face light, so controllable LED light. Good for the sort of darker vessels. This one was open to daylight, so not required. You can see down the bottom corner there the magnets, just permanent rare earth magnets that we use. And then these are called MC4000 tracks. So quite a lot of torque, quite a lot of pulling power, and then can pull crawlers and tethers a couple 100 meters down pipes quite easily, or can climb vertically quite well depending on surface conditions. And then out the front here is what we talked about. So that's the medium pulse eddy current probe. We use the standard probe for this because we're in a sort of dry environment, so no issues with having the buttons and that exposed. But we could quite easily change this out to a subsea system by just changing the probe, and the whole system could be used to about 30 meters underwater. So including the robotics, like not a huge jump there. We did use an encoder for the first part, for the photo. I didn't have the encoder on, so the encoder kind of sits out here, encodes directly into the lift system. that's just great for sort of keeping an accurate data, accurate pulse. We also have some tracking coders in there, so we know where we're driving. But pretty simple system, not the most complex. It was more just grabbing two different products, different companies, and making sure they work together and building a sort of platform. A lot of the work was done in-house here, just testing how everything would perform together. So like I said, this is the data. So this is actually the Excel data. This is what gets put out by the machine automatically. So after you do a scan, you can generate this report within sort of 30 seconds of completing your scan. But you also get the same sort of heat map and same sort of data live as well. But it's nice having it in Excel format. As you can see there, this is the only indication we found in the whole dissipator. It was right down in the news section. There was some blistering, and we found sort of significant corrosion there. So you're talking 30% wall remaining, and that was coming in from the external side, so quite significant there. But the rest of the dissipator was fine. What we were inspecting were pretty much meter squares. The client highlighted that in sort of screen planning, scan planning, pre-deployment. Yeah, so that's really it. A couple more photos of in the wall. That was a big isolation valve protecting us from almost certain death. And I guess the key thing here as well, that we're a technology provider, and these sort of scenarios might seem like we're doing a service, but we were actually working with the service company and the operator. So the guy here in the harness in the corner, he was the inspector, and he was there working with us to assess the dissipator and sort of take notes. We were really there just sort of proving the technology works. Since this job, that company has actually come back to us and asked us to train their guys now. So they were happy with the results, happy with the technology, and we're now training their team. So from now on, they can take these sort of solutions out themselves and sort of do their own inspection. We're always there to sort of help them and guide them through that process. That's really it on my end for the dissipator. I'm sure there's a few questions.
Jarred, just one slide back. I guess just for my interest, and just because we haven't explained it, if you don't mind just explaining percentages versus millimeters.
Yeah, that's a good one. So the pulse eddy current tends to works in a reference capacity. So what you do is when you get to an asset you're inspecting, you calibrate the probe to a nominal piece. You don't take a calibration piece with you like UT. You actually find nominal on the asset or near nominal that you can measure and adjust. And then everything is referenced back to that. So for this, we found some sort of nominal area up the top where there was likely not to be corrosion. We calibrated the system up there, and then we started our inspection. With that, you tend to get a little bit of margin of error. So you can see in there, there's a little bit of jumping around on the points, but it's not too bad. But with pulse eddy current, we tend to work in percentages for that reason. We find that because it's not a quantitative technique like UT, if you start talking in actual millimeters, people tend to get confused quite quickly about its capabilities. So we found it's better just to leave it in percentages and kind of explain it that way. The way the technique also works is that if you have extra supports or other backing material that's ferrous, that will start to show up. So we can see here, there were some supports that ran along, and the system picked those up quite well, and that's why we're getting areas of sort of elevated wall thickness. It wasn't an actual change in the steel plate, there's stuff there behind it.
Just a couple of other questions, Jarred. Maybe if you go one slide back, you mentioned the supports that you could pick up. Maybe just explain why the probe had to be set off a little bit from the, I know you touched on that briefly, but maybe just expand on that a little bit.
Yeah, cool. So what happens is, because we're measuring a magnetic field, if you introduce a magnetic field by having these, it's going to offset the probe's magnetic field, which is fine if it's a known magnetic field. Sorry, I'm saying that a lot, but I hope you guys get that idea. So what we're doing is generating a magnetic field, but we also have one permanently there. So what we found is by offsetting the probe far enough from the permanent magnet, we were creating enough of a decay from the permanent magnet that we would still see it with the probe, but it wasn't affecting the sensitivity of the probe. So if we brought the probe right under, we could still do the inspection, but it would kind of ruin the sort of sensitivity, because you'd always have this quite a high level of nominal, I guess, or quite a high level of magnetic sort of flux and sitting around your probe. So that's why we poked it quite far out the front. And that came quite clear in our testing, because the original concept was to tuck the probe quite nicely under the crawler and have it as a nice sort of small form factor package. One of the other sort of design features we did, and it's nothing crazy, but it just makes for a good inspection. UT, when you're using the probe, you kind of want to be sort of very much perpendicular to what you're inspecting. And if you have any sort of sway on that, you can tend to change your results. You don't get that with PEC, but we wanted the probe to kind of sit flush on the surface. But as we were driving over welds or bumps, there was enough bit of play in there that we wouldn't damage anything or break the housing. So we use those little sort of springs just to tension it on the surface, but also allow it to move freely over butt welds and those sort of things.
A couple of good questions coming through as well, mate. I don't mind jumping in with this one, but the question is mainly based around, okay, if pulse steady current is good for corrosion under insulation, obviously with this crawler being magnetic, it wouldn't work in that instance. Is there another system we could use instead when it comes to CUI?
Yes and no. Rick, you might actually be better to jump into this, but there are systems that we are developing with gecko feet and suction cup technology. The integration of the tool, of the sort of technique on the end, tends to be the easiest part. Actual driving around on an asset, driving to where you want to be, knowing where you are, tends to be the hard part. So it can be done, and we're working on sort of suction technology and things like that, where we could work on non-ferrous surfaces and then deploy electromagnetic inspection. I'm not sure if you want to add to that, Rick.
Yeah, I guess I just want to expand that. We're talking specifically about one scope here. It was ferromagnetic. It was a very, very thin coating, so that was okay to run the magnet through. But we also have a very large fleet of other robotic systems. So we can, as Jarred said, there's a couple of bits with sort of vacuum suction feet. So if there is a scope that comes up with CUI, depending on the diameter, if it's small piping in a pipe rack, for instance, or it's a storage asset that has some insulation on it, there'll be a different crawler for each application. So that's 100% then if it's a coating that's not magnetic, or the surface underneath isn't magnetic, or the insulation is such that you can't put magnets on it. There is a couple of other systems that would work perfectly fine for those, and then you attach the pulse steady current to that as well. Just in the same vein, I guess, Jarred, you briefly touched on this before, but why not UT in this case? Why would we use pulse steady current? I think you briefly explained the damage mechanism, and then you also explained the water. Maybe just explain those again if you don't mind.
Yeah, so there's actually a few reasons, and one I didn't cover is surface preparation. So with UT, you need, ideal situation is to have direct contact on a clean surface. So in this scenario, pull out a grinder, take off the top surface, take off any of sort of this rough coating, anything like that, and you just want to be on the bare steel taking a measurement. And with that, you need a couplant. So sound doesn't travel well through air, or well at all through air. So you need a couplant like a gel or water to bond the probe to the steel you're measuring, and that way the sound can propagate through the couplant into the steel and then back up through the couplant into the transducer. So for that reason, like, unless there's a real need or requirement for sort of quantitative, really accurate data, we sort of stay away from UT in these sort of scenarios, where having something like pulse steady current, where you can easily get the information you're after without the sort of level of accuracy of UT, but zero surface prep. A lot of times we find oil and gas specifically, we don't want to put couplant or leave any oil or gel in a vessel. And that's where things like pulse steady current come in handy. Yeah, so, but on that, we have design tools that can do surface prep and UT and deliver couplant. So we do go down both paths, but we find generally it's, you meet your requirements with pulse steady current, and it's a bit less work and a bit tidier.
I guess one of the key things with this was, Jarred, is the early engagement with the client as well. We had a chat around the UT side. We did have a chat about the damage mechanism. It was general corrosion rather than isolated pitting, which made pulse steady current quite an easy inspection to do for what they wanted to achieve with the damage mechanism.
Yeah. So again, I kind of didn't cover it too much, but with these sort of scopes, we have a sort of a wide range of expertise in our engineering team. So that goes from people like Rick, who are trained in UT. We've got guys who have done their doctorate in materials, who are phase array experts. We've got guys who are XRF experts, myself, electromagnetics. And we all sit around the table, we get these scopes, and we discuss what's going to give the best outcome for the client with the least sort of invasive approach, or and we're trying to sort of harness our whole team to deliver that, rather than just pushing one or the other. And that's kind of a sort of important upfront approach we do with just about all the complex scopes, is we gather the information from our clients or our prospects, and then we sit down as an engineering group and sort of vigorously review it and come up with an outcome from that.
A couple more good questions. I hope you're ready. This is another really good one. Magnetic hotspots. Maybe just explain a little bit on how the magnets are set off, maybe in the scan plan to try and avoid those. But if you've got a magnet running on carbon steel, is there any remnant magnetism left that might interfere with a pulse steady current signal?
That's a good question. It's something we tested here. The answer is yes. Like, if you're driving over, you're going to induce a magnetic field, and there's going to be some residual field left over. With this, we were talking sort of 19.6 mil plate, so very thick. And that residual magnetic field was so minimal, it wasn't an issue. If you're talking maybe a 3 or 5 mil thick plate, we would see that probably a lot more, and that would be an issue. Also, sort of to mitigate that though, like, we were happy with that approach, but also to mitigate it, we came up with scan plans. So the first part when we got on site was identifying the areas that the client wanted to scan. So they kind of walked through and highlighted areas where they knew there was potential for corrosion, and then visually they weren't sort of happy with the surface condition. And then from that, we created a plan of we'll drive here, here, and here, where we won't be driving over it and measuring the same spot. So it was more about sort of careful approaches to how we scanned.
We have seen that on thinner kelp plates as well in the past. If you leave magnets on a surface for weeks on end, you will see some hotspots. But yeah, if the surface is thick enough. It's quite an open question, Jarred. And I guess maybe we can expand on some of the other crawlers, but it's the maximum coating thickness for a crawler like this, and I guess maybe for the fleet in general. If it's a magnetic crawler, what sort of thicknesses have we done in the past, and what do we put in place for a thicker coating?
Yeah, that's a good question. Kind of a hard one to accurately, you might be able to accurately answer this, Rick. Off the top of my head, I think we've done up to about sort of a 3 to 5 mil coating, so reasonably thick. We can quite easily customize these crawlers to add extra magnets. We have magnetic bellies which we can screw on. We have dealt with these systems where we've kind of doubled up on them, but keep in mind that these systems can pull tether a couple hundred meters, these tracks. So we can increase the magnets and drive up a wall, and then we sort of reduce its range a bit. But we'll play with it and find the sweet spot. But sort of just off the top of my head on that one, and you might have a more accurate answer, Rick, I think it's about 3 to 5 mil coating, and we've increased the magnets to do that sort of stuff before.
Yeah, I think it also depends on the system. So there's obviously the track crawlers, which is what Jarred has on the screen, but there's also magnetic wheel-based systems where the magnet actually is lifted off the surface slightly. So it's essentially a floating magnet, which helps if there's coating roughness and wells to go over, but obviously you do lose a little bit of your magnetic pull. So then 100%, as Jarred said, the coating suitability for something like this where there's a floating magnet would be less. But there's also some other systems in the fleet where the wheel itself is magnetic. In that case, you'll have a thicker coating you can travel through. Well, then exactly as Jarred said, there's actually one scope very recently where we essentially just doubled up on all the magnets to be able to scan through. But the last step should also be, do we need magnets? So there are systems that if we don't have a ferromagnetic acid, let's steer away from magnet, even if it's a stainless, so maybe a low ferro. If it's a stainless, do we need something that's magnetic? Why don't we go down the path of a vacuum style system? There are other deployment methods as well, rather than just going magnetic. I guess an interesting one that maybe you didn't mention as well, Jarred, I'm just thinking about it now, the thinner the ferromagnetic material would also affect the thickness of the coating. So if you're inspecting an acid that's, say, 4 to 10 mil thick with a coating that might be 4 or 5 mil, that would have a completely different set of restrictions compared to an acid that's maybe 20, 25 mil thick with the same coating. Just the way the magnets work as well. But yeah, I think the first question is, okay, do we need to use magnets? And if that's the case, we build factory acceptance tests. So before any of these jobs go out, we'll have a factory acceptance test in-house. If a client's happy to share the wall thickness, the material type, and the coating type, we set that up in-house. If we're doing a 12 o'clock inspection or we're doing a 6 o'clock inspection, we'll set it up in-house, share that data, and make sure we're ready to go to site even before we arrive on site. At least we've tested it and the client's happy as well.
It's also, just to build on that again, Rick, it's also payload and scope dependent. So what are we trying to achieve? Are we, after a visual inspection, do we need extra tooling on it? So there's those sort of questions. Most of these scopes have their own challenges and own requirements. So it's all, we start by reviewing the drawings and reviewing the damage mechanisms and the scope, and then using our sort of team and expertise to come up with a sort of best proposal, best solution.
Yeah, unfortunately, it wasn't just a fixed value. It depends on a few things, but I hope I answered the question at least. There's a couple more questions, Jarred.
Cool.
I'm wondering how we share this one. This was an anonymous question, so I'm not actually sure where this came from. But it's more based around, can we share some data from what we've received from the camera? I think we'll probably take the other approach. We don't want to share client data, but we have done factory acceptance tests for these systems. We do a lot of trials in-house, so there's a team that works on resolution charts and comparing different cameras for different applications, depending what the damage mechanism is, making sure we've got the correct line pairs per millimeter to make sure we can pick up an asset. More than happy to share that data of any one of our cameras, depending on the application. But if you don't mind just sharing, maybe get in touch with myself or Jarred just straight after, just because I can't see who asked the question. But more than happy to share some camera photos specifically to this, but then also the other cameras as well. Have you got the general webinar slide, Jarred?
I actually didn't put it on this. I just realized.
Okay, no worries. Maybe just share a couple. I don't know if you know the next few that's coming up over the next few weeks. I know some of them.
Yeah, I believe we're doing the SAR.
Sure.
So the SAR is a robot that was, we brought it in as a sort of a beta test, a trial. It was developed in Saudi Arabia for Saudi Aramco. So it's a wireless dry coupled UT crawler. It's got quite a, I won't sort of give the end of the movie away, I guess, but it's got quite a unique drive mechanism, and it's designed to sort of external on pipe racks, drive along pipe racks, and sort of perform UT. It's wireless and that. So we've had that in. We've been doing some testing. We've got some great footage of it, great data on it, and I think next sharing that in the next few weeks. I'm not quite sure what the next one after that is.
There's also some on the Magneto side of things, so that comes up on the 28th of June. Thanks, Scott. You just shared that, mate. Appreciate it. But yeah, so Magneto's on the 28th of June, so that's a multi-limb system. For those questions that came through for CUI with a thicker insulation, that'd be a really good one to join because we're currently working on some vacuum feet for that system. So that's a perfect solution. We can add the pulse eddy current system to the front, and you can climb from one asset to another, do sort of medium ball piping, sort of 4, 6, 8 inch and up, but also do storage vessels. So there'll be a discussion on Magneto on the 28th, and then correct, as Jarred mentioned, on the 4th of June is the SAR, which is the wireless crawler. I'm not sure if there's any other questions. Otherwise, thanks for joining. Appreciate it. We'll share on LinkedIn again when the next ones are. We'll give a couple more minutes if there's any more questions. Jarred's details is on the first slide if you want to get in touch. Otherwise, just find the office as well. I'm not sure if there's anything else from you, Jarred.
No, I just encourage, like obviously there's some good questions. My details are there on the first slide. If anyone has any questions or follow up or wants to go into pulse eddy current or any of the sort of topics we're talking about a bit further, feel free to contact me. But yeah, appreciate everyone coming. Thanks.